We are ready to move on to the next talk, which is going to take place remotely. Okay, so this talk is a recording that Naman prepared for us. We have one of the co-authors here in the audience at the end for taking questions from us, okay?
Hello everyone and welcome to this talk. I'm Naman Kumar and this work is co-authored with Yash Kondi and Hernan Venegas. I'm from IRIF and Yash is from Silence Labs and Hernan is from Hashbook. In this talk, as the title suggests, I'm going to be talking about threshold signing for standard hash-based signatures and some problems that you encounter while you're doing this. So just to give some motivation as to what I'm going to be talking about, we start by studying hash-based signatures from a theoretical perspective. And in particular, the reason why we want to study this is because in light of the new PQ standards, we really want to understand what is the feasibility of threshold signing, the new post-quantum signatures that we have. And in this work, we're going to be studying the feasibility of like threshold signing hash-based signatures. Just to give an outline of how I'm going to proceed. First, I'm going to give some introduction and some background. Then I'm going to introduce this new definition of extractability that we have, which allows us to prove many things, including various impossibility results. And then after that, I'm going to talk about what conclusions you have to draw from this, because as the title suggests, they aren't exactly super positive. Okay, so just to review what a hash-based signature even is, this is something that is kind of important to define because hashes like make their way in pretty much every kind of signature. I mean, Schnorr and ECDSA use hashes, but of course they are not post-quantum signatures or hash-based signatures colloquially. The idea stems from this Lamport's one-time signature scheme, which has a secret key, which consists of two randomly sampled values and a verification key, which is the hashes of those values. And there's a signature scheme which allows you to sign a single message. So in this case, the message is a 1-bit message, and what it does is, and the signing algorithm is like really simple. All you have to do is reveal the pre-image, and then after that, the verifier can simply hash and check if the hashes correspond to the verification key. Now, of course, it's only a one-time signature scheme, right? So the question is, how do we extend this? And the idea is to use Merkle-style constructions in order to extend this to, so that it can be used again and again for a variety of different messages, and furthermore, so that you can also, sign longer messages. But yeah, they all follow this like tree-style technique, which vaguely resembles a Merkle tree. Of course, the big upside of hash-based signatures is that they use only one object, which is a cryptographic hash function, so SHA suffices. And in particular, some examples of schemes are XMSS, Sphinx, and Sphinx Plus. Sphinx Plus, in particular, is actually an accepted, NIST standard called SLHDSA. And crucially, as I said, the advantage of this is that the signature security reduces only to a single cryptographic primitive, which is a hash function. And naturally, if you want to study this theoretically, the idea that we can use, of course, is studying this object in the random oracle model. Okay, so the working definition of hash-based signatures we're going to be using is this security reduction requires no hardness outside the random oracle. So ultimately, all your security follows from the random oracle. Okay, so we've talked about what kind of signatures we're dealing with. Now let's talk about what kind of threshold signing we're dealing with. So in general, of course, it's simple. You can sign basically any, you can sign basically any signature in a threshold manner just by using generic MPC techniques. So in this case, you represent the signing algorithm as a circuit. Take in shares of the secret key and then like sign for any message of your choice and obtain a signature. Now, of course, the downside is if you want to do this, you're going to have to evaluate SHA inside of an MPC, which is like very expensive because of the large number of gates. And in fact, if it was simply one SHA evaluation, this could be kind of feasible. But even XMSS uses something like something in the order of thousands and thousands of SHA evaluations. So of course, this is going to be a bit too expensive for us. In general, we prefer if all of our Oracle calls are black box, which means that the Oracle calls are simply made by each of the individual parties during signing, and in that case we can get significantly more efficient MPC protocols. So the setting we're going to be studying is one in which parties make only black box use of the random oracle, and in particular we call this oracle respecting distributed computation. So here is a brief overview of our results. We start by defining an extractability property of hash-based signatures, which is borrowed from physics. After this, we use this extractability property in order to prove that we can actually rule out all but one signing protocols for, this Oracle-respected computation of extractable signature schemes. And the model that we're going to be working in is the one with no CRS, no dealer, and no pre-processing. I'm going to talk about that in a little bit. Okay, so let's recall the notion of NISX in the ROM, because this is where the extractability property is most significantly motivated. So if you recall, in the NISX, there's a prover which has, which makes a certain amount of queries in the case of proving something, and in particular, this proof is usually something of the form that, it has some witness X, which is, it has some witness to a statement X. And of course, because it's a NISX, this has to be witness hiding, and so the prover, it performs a set of Oracle queries and then sends these over, sends a proof over to the verifier, and the verifier checks it. Now, in particular, we call a NISX extractable if there exists some extractor algorithm E, which, given a correct proof, it can actually use the queries that the prover made and use these queries in order to be able to extract a witness. This is a straight line extractability. And similarly, we can define extractability for signatures as well, in which, instead of a proof, there is a signature, a message being signed, and, the way this message was signed produced, a certain number of Oracle queries, and given these Oracle queries, it's actually possible to find out, it's possible to obtain some information. The secret key in our formalism, in fact, is that it's possible, given these queries required for signing, to produce a new signature for any message of choice which verifies. So you can forge a signature given the Oracle queries made. And this is our definition of K, T extractability. So T is a parameter that is used for more fine-tuning and becomes important when we're talking about pre-processing. But for now, you can think that we call a signature scheme K extractable. If given K signatures, you can use the Oracle queries made during those K signatures in order to forge for any message of choice. And this is a good definition because as a check for whether this is a good definition, we can see that K, infinity extractability, this just reduces to unforgeability. So, it's well motivated, reduces to a security property that we have studied in depth. Now, what happens, of course, in the real world is that we don't just have signing algorithms, we also have key generation algorithms, and this is often distributed as well in the threshold setting. So for something like Lamport in particular, the previous definition doesn't even really apply because it's possible to sign with zero hash queries. So we also define fully extractable signature schemes, which are essentially the same idea, in which case, you're allowed to, you can forge if you're also given the queries that were made during key generation. So this is a slightly stronger definition. Okay, so as I said, we call this is our extractability definition, and in order to see if this definition is actually useful, or if it's something that makes a lot of sense, we want to check if common hash-based signature is extractable. And this can be proven easily for XMSS or Sphinx Plus. All of these signature schemes can be easily proven to be extractable. And I'll give you the intuition, which is that all of these schemes, the atomic unit of the signing, is actually Lamport. It's Lamport-style signatures. So Lamport is an extractable signature scheme. We can show this quite easily. And all of these schemes use Lamport-style subschemes. And in particular, the reason why Lamport is extractable, because if you have no hardness outside the random oracle, then basically the only thing you can do is hide the queries. And if the queries are revealed, then of course you're going to have a problem. Okay, so what is our impossibility result? And let's show this for the extractable setting. So if you have an oracle respecting protocol for signing, this is our protocol. We show an attack against this, which is an oracle respecting protocol for signing any hash-based signature scheme, which is extractable, and the attack is as follows. So the parties produce a signature, so you allow one iteration to pass, and it's in the all but one corruption setting, so the adversary has corrupted all but one parties, and now the adversary gains access to all these queries that it has obtained. Yes, and using this, the adversary's goal is to, of course, produce a new signature for a message of its choice. So now the adversary has access to all these parties' queries. What the adversary can do is now it can view this distributed signing protocol as basically a regular signing protocol occurring inside somebody's head, and the adversary has access to all but one of the parties' queries that was made during this. And in particular, The definition of extractability implies that a scheme is extractable and every other scheme which has the same verifier is also extractable. So in particular, this new scheme which is working in the head is also going to be extractable. So the Oracle queries will allow you to forge a message for this scheme, but this scheme shares the same verifier as like the distributed scheme. So this is the setup. And then what you do is now we have this like in the head scheme, and we can simply run the extractor for the in the head scheme to forge. The crucial downside here is that you actually don't have all the Oracle queries that were made. So if you recall, the definition of extractability requires you to have all the Oracle queries. Here you have all but one party's Oracle queries. And the key technical content of this paper is actually how we can like use this in order to be able to still forge. And in particular, we take this, we reprove something for our setting, which was originally a technique that was in this paper from Crypto24, which proved the same thing for like schemes which are MPC in the head base. So in particular, we proved this lemma which says that if you don't have if there are some queries that you don't have, it's possible to actually simulate them given that the number of parties is large enough. And you know, you can still succeed with some inverse polynomial amount of probability. How big is this n? Well, in particular, the n has to be greater than the number of queries made by the verifier, so this can be thousands to tens of thousands of queries in practice. So our result rules out, like completely rules out any kind of like Oracle respecting signing schemes if you have like a very large number of parties. Of course, the natural question is, hey, what does this say for two parties? And the problem is, this is still not looking particularly good. So so in this setting, the idea is a bit more nuanced, which is that you know if you have schemes like Sphinx or Sphinx Plus, they usually have like an important hash query that cannot be leaked. In particular, these schemes make use of a PRF, and you know. The problem here is that if the key of this PRF is like revealed, or if if a query is made which has this, then this is going to be able to basically break the security of the scheme. And for two parties, this means that you know if you corrupt one party at random, then you know whatever signing protocol you have, somebody's going to have to make a PRF query, and then you learn with something like half probability, you just like end up learning the key, which is of course something that we cannot accommodate. We also have a proof for the pre-processing model, and the schemes, and this proof says that you know any scheme which Oracle distributed, which in a distributed manner computes signatures for k messes requires at least k steps of pre-processing. So the amount of pre-processing that you have to do is linear in the amount of signatures you have to sign, which doesn't bode well because if you basically have to like make an unlimited amount of signatures, then you have to like essentially do almost an unlimited amount of pre-processing. In particular, I think there are some results out there which like use pre-processing to like sign hash rate signatures, but their numbers aren't great. It's something in the order of like 3 to 4 gigabyte long common random strings, you know, and like other kinds of like pre-processing, which is like not particularly great. So all that's to say that the conclusions that you can draw for this are the follows, which is that you know if you really want to sign, if you really want to perform threshold signing in the post-quantum setting, then hash-based signatures are not really the schemes that you should be looking at, and they have the following, and you really should consider the following problems that we now show, which is that the protocol has got to make either non-black box use of the hash function, so that means that you have to evaluate SHA inside MPC, or you have to use like structured algebraic hashes, you know, which support efficient MPC protocols, but these are going to make your actual signing process a lot slower because none of these are as like, you know, the actual hash function is like not as good as SHA. And of course, you know, this will be fine if you're just making a few of them, but like if you're performing something like, if you're signing something like Sphinx Plus, you might have to make something like 1 million hash queries. Secondly, schemes, you know, if you want to do some pre-processing, then, you know, and if you have access to a trusted dealer, this is better, but the amount of pre-processing that you have to do is still not particularly small. So this is unsuitable for application where such a dealer is absent unless, you know, you can compromise on efficiency. So the question is, what if you simply use generic MPC? Well, we've done some basic estimations, we have run some numbers, and here's what we get. So if we use XMSS for these two parameters, and we're using a garbled circuit implementation of the EMP tool library, in this case we're simply using you know, 2 garbled circuits in order to sign dual execution MPC. Then if you want to compute the WOTS function, which is like a unit that is used in XMSS, it takes something to the order of 316 milliseconds. And in particular, this is not great, but you have to do this again and again and again and again, and this really adds up. For Sphinx Plus, the numbers we have are like completely horrible. In fact, it comes up to something like 20,000, you know, seconds when they have garbled techniques. So of course you can like these are just some basic numbers where we're just throwing like, you know, just like ready-made tools at this problem, and of course you can, if you think more cleverly, you can probably come up with like better signing techniques, but at the end of the day, you will have to evaluate something inside of an MPC, and this evaluating this is going to be like particularly problematic, and is going to like you probably won't take 20,000 seconds, but like even 20 seconds is not a very good number. Okay, and with that, I'd like to thank you for this presentation and listening to this talk.
Okay, so we have a Yashvanth here for questions, in case anyone has any. Do you have questions from the audience on this paper? Yeah, maybe I ask one. So this is showing specifically that hash-based constructions as we know them cannot be run in MPC without running the hash function in MPC, or in general, any hash-based construction, not just the ones that we know. I don't know if the question makes sense. It's just like looking, for example, at MLDSA is like they are trying to target a specific construction, and I wonder if you tried deviating from those existing constructions to try to find one that minimizes the amount of hashes you have to run in MPC.
Thanks. So at least the analysis that we do is for specific specific signature schemes at the moment. There are some bottlenecks that we run into when proving. So the starting point for this result was this previous paper from crypto a couple of years ago that showed that for NISIX at least, you simply can't construct NISIX that will allow for efficient distributed computation, and we were trying to prove something similar for this. There are some barriers. It seems to prove a more general result. You can, for instance, design schemes that have a threshold kind of baked into the scheme, like the number of signers or whatever baked into the scheme. As of now, we don't rule out constructions that may support efficient MPC, but seems extremely unlikely. Like the fundamental barrier that you have to get around is this extractability definition, right? So, yeah, does that sort of answer the question?
Yeah, perfect. Thank you. Okay, so in that case, let's symbolically thank Naman again.